So, good afternoon, everyone, and thank you all. Thank you, Patrick and guys, for inviting me. I will present. I will outline a research topic that we are investigating, and it is a collaboration between University of Palermo and Temple University. And in my talk, I will briefly outline some of the ideas we are considering in this kind of collaboration, while in the subsequent talk, my colleague Francesco Lanza will outline more, will enter more in detail in the implementation aspects of these collaborations. So my talk is more high level, let's say. The general topic of the general scope of our collaboration is really put in real rough words to embody NARS. So to have some sort of embodied version of NARS in a robot. A main aspect of this problem is, for example, to understanding scenes. So a robot interact with people. There is a scene which is made up by people, made up by object, and the robot should be able to really understand the scene. So should try to understand the situation. A main point in this kind of research is the role of the focus of attention. We live thanks to the focus of attention, of course. So we want to understand scenes by implementing a kind of focus of attention which should be driven by expectation. And another goal of our collaboration, as I said before, is to embody NARS in a sensory motor perception system. The general goals of this project is to, as I said before, to allow a robot to navigate inside a scene, to generate expectation about perceived scene, to implement some predictive planning techniques, and the robot should also be able to imagine the effect of the interaction with object, possibly before performing any kind of action. So those are the aims and scope of the project, of the collaboration between my laboratory and the group of Temple University. Okay, according to the principle, to the AIKR principle mentioned before, even by Chris, the role of focus of attention is obviously an important one. In fact, a finite agent has limited resource, and so an agent cannot carry out a one-shot exhaustive analysis of the data coming out from the scene within reasonable time. So there are time constraints, there are memory constraints, and so on. Because, of course, some collected data and the relationship between data are more relevant than others. So it would be a complete waste of time of computational resources to detect useless details. So in order to allow a robot to understand scene, it is necessary to implement some kind of sequential scanning that acts as a kind of focus of attention. We take some inspiration from the biological focus of attention, but up to a point, I can say. From the psychological literature, a focus of attention is generally described in terms of a spotlight beam that scans the visual field. Very simply, a very simple view of seeing the focus of attention is a kind of a beam. So objects falling inside the spot are processed. There is some computational resource allocated to the objects falling inside the spots, while the other objects are ignored. this is a very simple view, of course, of focus of attention, because subsequent theories consider the fact that there is a space-based attention, in the sense that attention may select even empty region of a scene, or the focus of attention may select region containing object of interest. And there are, of course, some kinds of hybrid theories of the focus of attention, which are, according to these hybrid theories, the focus of attention is partly based on space, partly space-based, and partly object-based. Anyway, all the theories of focus of attention take into account the fact that the focus of attention is typically a serial process. It's a process that series is based on seriality and selects only a few items at a time, and it moves from one object to another. I may remind many computational model of the focus of attention. The most famous one is mostly the saliency map by Etienne Koch. Okay. In our view, the role of the focus of attention is driven by expectation. So we imagine a system, a NARS system that generates expectations, and the focus of attention then is driven by this kind of expectation. So the focus of attention may select relevant aspects of a scene, which may be represented by a set of low-level assertions, and the expectations are generated. In turns, these expectations look for specific aspects of the scene, and then assertions are added to the NARS knowledge base. Of course, not all true assertions are generated, but also these the assertions that are judged to be relevant based on the attentive processes. And in these aspects, the ideas of all the ideas related to the certainty, related to the frequency and to the priority, which are inside NARS, are very useful, because it is able to, all these mechanisms are able to weight the usefulness of assumption, not the fact that assumptions are true or not, but the fact if the true assertions are useful or not in this general framework. So, for example, when the vision system of our robot, we use one of the robots that we employ is the Pepper. When the vision system of the Pepper is useful at recognizing a single object, which may be a component of a more complex object, let's consider, for example, the hammer. And the focus of attention looks for a cylinder, which may be the handle of the hammer. Then there is an expectation is generated for an hammer, and then the focus of attention looks for the other part of an hammer, the hammer head, for example. A similar example may be a chair, for example, or a person. So if the focus of attention looks for an object which may be a leg of a chair, then it looks for it generates an expectation of a possible chair, and then it looks for the other aspects or the other parts of the chair. So in this case, there is some casual beginning, in the sense that a big object, for example, captures the focus of attention. And the focus of attention starts by generating expectation, and this expectation generation is useful to drive the focus of attention, so the search for the other useful objects. So, for example, considering a network router. So we work in a computer laboratory, so we have many network routers. So, for example, initially the robot center its focus of attention on a pattern of pixels. So which corresponds to a set of low-level assertion in NARS, or a pattern of pixel representing, for example, the body of a router, so a box. This simple, the fact that this is a simple object, which is a box, may be consistent with the fact that this box may be the body of a router. And then the focus of attention, we generate expectation of a router, and then we scan the neighborhood of the object in order to find a couple, for example, of thin antennas, of thin cylinders, which are the antennas. And in this sense, the system eventually generates the recognition of a router. And the fact that there is a box, there are two cylinders, which has the role of the body of the router, and two cylinders, which have the role of antennas, in some sense, alter the frequency, the expectation of the fact that there is a router. So once the system generates an expectation, this expectation is satisfied. In some sense, this fact has a role in the frequency, in the certainty of the whole system. So this is a very simple example. The very simple example I mentioned. There is a box. The box may generate the expectation of a possible router, but the router is made up by something which is a box and two antennas. So there is a generation of an expectation, something which may be a cylinder, which has the role of the right antenna. The right antenna is found. Then the robot looks for a left antenna, and so on. And then a router is recognized in terms of a box made up by two parts, which are related to some with some geometric constraint, of course. In this sense, the system recognized a complex object in terms of expectation generated. Of course, the generation of expectation might be driven by for example, by the context. We take into account two kinds of sources for the of expectation. So where do expectation came from? We take into account two general sources. One source is what we call a kind of linguistic expectation, in the sense that somewhere in the database, in the knowledge base of the robot, there is a description, a kind of dictionary. There is a description of a router as something which is made up by a tick box and a couple of thin cylinders with some characteristics and some relationship. And then, because a router is defined in this way, so a kind of prior knowledge, let's say, something like this. And so in this case, a router is described in the knowledge base of the robot as a kind of in this way. And then as soon as an object is recognized, which is a part of a router, then the system will look for the other parts of the router. And in this way, you may also consider, for example, more general description as a context, as I said before. For example, the context of an hardware store, or the context of a robotics laboratory, which you may expect to find objects related to a robot, and so on and so forth. And another source of expectation might be the associative expectations, in the fact that suppose that the NARS learned that when there is a router, there is also a cable which is plugged into the router, or together with a router there is an hammer, because in the laboratories, in our laboratory, there is a router and there is also an hammer. Then the robot the robot learn to associate this object. It is more a kind of associative expectation. So it's not related to the general description of a router or general description of an hammer, that a hammer is close to a router or a fork or whatever. But normally during the life of the robot, let's say, the robot looks for the robot learn to the association of these two objects. Let us consider the fact that this problem may be related to the hot problem of bias, which is a really hot problem in every kind of learning system, the problem of bias in training sets. Anyway, the border between these two kinds of expectation is not crisp in some sense. So let's say that the linguistic expectations are mostly related with a priori knowledge, with the prior knowledge of the robot, while the associative expectations are the knowledge learned by the robot during the life of the robot itself. Okay. The level of certainty in NARS are important in this scenario, because only the most relevant expectations are taken into account, and this is in some sense may be related with the frequency in NARS. And moreover, when an expectation is satisfied, the certainty associated with the object and the part may be revised, in the sense that this may be related to confidence, for example. So in the sense that if I really confirm the fact that there is a router, then the full confidence on the object and is changed in some sense. So the fact that there is a box, there are two cylinders into situation, into position, and so on and so forth. So the level of certainty, how NARS treat the concept is important, because it is the role of relevance, the role of importance of the entities to be considered with respect to other entities is important in this kind of scenario. So, as I mentioned before, a robot is a kind of embodied focus of attention. So in our experiments, we use a paper robot and a now robot. So the focus of attention is driven not only by considering a camera moving and so on and so forth, but a physical object, which is a physical robot moving into the scene. So the focus of attention is related to the movement, to the body motion, of the robot. So, for example, when the robot finds a router, it may physically move its own body and its own head to search, for example, for a cable attached to it. And so the robot will explore the scene, is inside the scene, and will explore the scenes driven by the focus of attention controlled by the system. In the case that expectations are not satisfied, for example, in the case that the robot finds a router with one antenna only, or a router with a detached table, for example, the robot might alert a supervisor or whatever. So we have to consider also the fact that expectation might be satisfied, but expectation might not be satisfied. In this case, the robot should take into account the possibility to consider alternate routes and so on and whatever. The important thing is that the movement of the robot might be, so the generation of expectation allows the robot to imagine or to simulate the possibility of interaction before the robot really move into the environment. So the robot may imagine and so may reason and anticipate future interaction with the object in the environment. So the interesting part is that generating expectation, if you generate expectation, you may reason about this expectation. In this sense, you may also generate a random expectation, and even physically impossible expectation, You may reason about, like in case of dreams, for example, which you generate expectation which may be physically impossible in some sense. So the robot might expect to fly, for example. So in the case that there is an obstacle, the robot may generate the expectation on avoiding the obstacle by flying, which is something that happens during dreams, for example. So the robot might not only generate expectation and reason about expectations, but the robot may also generate physically impossible expectations, and the robot may also reason about impossible expectation. But this impossible expectation may have a role in the knowledge base of the system. This is a huge, strange topic of the role of dreams in our cognition, and maybe there are some counterpart in artificial cognition. Anyway, an important part of this general project is to investigate the role of imagination, the role of anticipation, and even, let's say, the role of, dreaming. So imagine random interaction, physical interaction, not physical interaction, and so on. So predictive planning is planning by imagination. So the robot, in order to reach a goal, may generate expectations on possible interaction with the environment and choose observing the desired input and choosing the right way, the right path by taking into account the reasoning about the generated expectation. So the predictive planning is observing the desired input, considering the goal, considering the environment, and to generate expectation that take into account even adversarial conditions. So, for example, the lack of knowledge, the lack of appropriate model, conflicting goal, redundant goal, and so on. So predictive planning is planning driven by imagination. So, for example, a trivial example, in the case of a missing antenna, the robot can generate a plan to search for another antenna. Pick up a new antenna and mount it on the root. So in the case of predictive planning, the robot may imagine may generate a goal of searching for a new, may generate a new goal. So search for another antenna in the environment and to pick up the new antenna on the root. For example, in the case of a simple case of block words, the robot may imagine an higher tower of blocks, the good old blocks word. The robot may imagine a tower of blocks made up for 4 blocks, and then he may imagine the fact that the robot should pick up the red block and complete the tower. In the case, the focus of attention is dreaming by the search of a new box, because the robot imagined the possibility to put another block to the block tower. Going further, we may imagine the possibility of considering dynamic scenes. So the generation of expectation may not only be related with objects, so for the fact that there is an object and you can complete the object, as in the case of a chair, as in the case of a block tower or whatever, but also considering the action of the people in a scene. So for example, if a person is grasping an object, maybe the robot may recognize the action of grasping, and then the robot, for example, may change its own position to get the object grasped by the other person, for example. Or the self-monitoring. So the robot may imagine and may recognize the action performed by its own body, like if the robot looks at itself from the outside, for example. So if the robot is able to recognize the action from simple actions from another person, it may also recognize and reason about its own action. And finally, a really intriguing goal concerns the concept of affordance. So do not recognize an object because of the shape, but recognize the object by the action to be performed on the object itself. Like, for example, the case of a chair is typical. So you recognize a chair because it's something that you can sit on. So it's difficult to define the concept of chair. But a chair may be considered by taking into account the actions which are related with the option. So a further investigation in brief, might take into account the typical problem of recognizing not only objects, but recognizing action performed by external people, by other people, by the external environment external to the robot, but even to the robot itself. Okay, I stop here, and thank you for your focus of attention, for your